Hi, good evening. I'm Dr. Philip McMillan, and today I am taking you through a piece of information that oftentimes I think has gotten lost by much of the scientific community about the interaction between SARS-CoV-2, that's the virus that causes COVID, and bacteria. When I first saw this research, it was mind blowing, but this is all the way from 2021. So, what happens is that people then kind of forget about it and they kind of think it's not so relevant. But I was recently in a discussion, kind of, where we were talking about this issue about the lab origin and whether or not it was natural. All I can tell you is the stuff that this virus can do I have never seen before. I can't find anything that is able to do what this virus can do. So it is possible it's just random. And I mean, coincidences happen all the time. But whichever way we take it, we are dealing with something that is incredibly frightening when you think about the long term implications of it. So I'm going to take you through the paper in 2021 because they've just released another paper. But in order to understand the other paper, I have to take you back to what they did in Italy in 2021. So the important point is that whatever you do, please do not underestimate infection. And so, what I'd ask you to do is before you go anywhere, make sure you click on the subscribe button. If you don't see the button, there is usually an area just to the right of the screen here where you can see a bell. Just click on that. The next thing I want you to do is I want you to make sure you look in the description below the video and you make sure you get our free ebook. It's free. And the reason it's free is because this is so important, nitric oxide and the sinuses. And what you can see here is that we've done this, and we did a whole book on Amazon about humming heroes. What we're trying to highlight here is that if you protect this area here and prevent the virus from breaking through your mucosal immunity, it reduces the risk of some of the frightening things that I'm going to be talking about now. This is free information. Please, you will also get links to our newsletter, which we will be able to keep you up to date on. And so make sure you click on that link before you do anything else. This is the landing page you'll come to, and you'll join our newsletter. But let's get back to the science. So I'm going to take you through this very important paper. And as I said to you, it's from 2021. And Dr. Carlo Brogna, I've interviewed him before, and I'll probably do it again. It's sometimes difficult because of the language barrier, because he's Italian. But it's this piece of research that he did with his team, and this is Carlo Brogna here, about looking at SARS-CoV-2 RNA load in fecal samples, that's in stool, and they say prompts rethinking of the biology and epidemiology. And you can see here that this piece of research was done first published in May 2021. Now, you can imagine around that time, everything is about the fact that we've got vaccines and the vaccines are going to stop the pandemic. And I think that this piece of research got lost. If I'm quite honest, even I sometimes forget that it's there. I always think about it and I always present around it, but I don't really talk about what it was that they did. So, just to give you a summary as to what it was they were doing, this was around the time that we were noticing that SARS-CoV-2 was in the stool. And so they were talking about the fact that there could be involvement of the human microbiome in the development of the disease. And so they were looking for the presence in fecal samples. So they were one of the earliest people who identified SARS-CoV-2 in fecal samples. And just to be clear, when we say that, we're talking about the wastewater measuring. So in some places, still in the US, you can see that they can observe the trend of infection by the fact that they can see higher loads in fecal, in sewage. And so they know more people are infected. So it's on the rise again. And so this is how they are aware that more and more people are getting infected. So it is tied to this piece of research as well that we know what was happening. So what they did is that they designed a test to cultivate the microbiome from infected people and to look at the viral load and collect the data. And that's what I'm going to be taking you through and show you what is really, really some remarkable insights that they had from 2021 that people don't quite understand is happening now. So I'm just going to take you through some concepts in a little bit of a slideshow, and I'll hopefully get the points across as to what I think we need to be looking at. The first thing that you have to remember, and this is why I'm telling you about making sure you protect your upper airways against the virus. Hum along if you can. If you don't believe me, do it anyway. But the point is that we can see here the human body, and I have here the point about viral dissemination. So the virus will infect here, but once it breaks through the mucosal barrier and gets into either the bloodstream or the lymphatic system, it's going to then circulate throughout the whole body. And that's what we call a viremia. That's when people tend to feel a little bit achy and sick when the virus is in the bloodstream. But one of the first places it goes after going down to the lungs by you breathing, it heads to the intestines. And that's because there's a lot of ACE2 that it can bind to and therefore infect cells in the small and large intestine and replicate. And actually, the more I look at some of the changes that occur around the immune system with IgA levels being very high, I'm beginning to think that this part of the infection early on is probably the most significant cause of the viremia that occurs in terms of severe COVID-19. So we think it's all about the lungs, but actually the immune system could be being driven from the gut. Now, in a separate paper that this same group did, before they did that, they were looking at the fact that they were finding abnormal bacterial toxins in stool, in blood, and in urine. And so the question we had at the time, and this is where this slide is trying to put it across, is how in the world does that happen? So I've got here a bacteria, and this is the bacteria here, and it's a question mark because this can happen, it seems, in relation to both vaccination and infection. Is it that somehow the lipid nanoparticle can get inside them? Is it just that spike protein can get in them to make them produce toxins? Or is it the virus or pieces of the virus that get into certain bacteria and make them produce more toxins? We'll come to which bacteria we think is the main problem in that context. It's not all of them. And actually, some of the research done by a Dr. Hazan in the USA has demonstrated that some of the good bacteria get completely wiped out after infection and vaccination. So we know something is happening in between the toxin productions. And the way that it would work is something like this. If you then have bacteria producing more toxins and more dangerous toxins, they will then start to target the good bacteria in and around the gut. So these bacteria will get stronger whilst they continue to destroy the other bacteria around. And so it would look something like this. So these are I have now, this is what the bacteria would look like. It's producing all these toxins. These are some of the other ones, especially the bifidobacteria. Literally, as Dr. Hazan says, it goes to zero. And this is one of the very important bacteria that helps to break down some of the, especially vegetable material in your gut and produce butyrate. So these are very important, good bacteria that get completely decimated in around infection and vaccination. What is happening is that we don't quite know exactly how this is occurring. And so, what we would then see, and I'll come back to that, is that you can have certain diseases like Clostridium difficile, streptococcal infections with more toxins, and generally bacterial overgrowth could all happen in the context of this kind of situation. So, now with that background, I'm going to take you back to the paper and I'll show you what it was that they were doing. So I'll have to jump between the paper and some of my slides. So what they decided that they were going to do is that they were going to get some samples and try and work out what was happening with the viral RNA. So here is the methods that they used. So they then got some stool, fecal matter from somebody who was infected. They put it in a specific nutrient broth and they let it grow for about 14 days. And then they were checking to see if there was change in the context of the viral RNA. At the same time, they got another sample, which they called sample B, which was from somebody who was uninfected. And they needed that to be their control to say, well, do we see any changes in stool RNA in somebody who is not infected? And then what they did is they then inoculated some of sample A, the supernatant from it, when it was spun down, put it in sample B, and they then tried to see what was going to happen. So I'm going to try and see if I can show you in images here, because sometimes it's hard to get the concepts across. So I'm going to show you here in images what essentially they did. So as I said, they had sample A, and sample A was somebody who was infected. So they put their stool in there and they then special broth so that the bacteria can grow and still live. And therefore, if they're going to produce more RNA, they'll be able to do it because they have energy. They then got another sample from somebody who was uninfected. This is sample B. This person had normal stool put again in the culture broth, and what they were doing was checking to make sure that if they see increased RNA in this one, they don't see it in this one, because then how would that make sense? So they checked to make sure it wasn't anything else that was causing it. Then what they did is they combined them. They spun this down, took some of this, put it in this, so they made another sample, and this was sample B plus A, because they were trying to see, well, if we're seeing viral RNA in this one, can you therefore infect a normal stool sample? And so that's the essence of what it was that they were trying to do at the time. And so now you have to look at what happened when he did that. And I broke that down so that you can see the sample A, sample B, and sample B plus A. And then sample C, they said it was just the pellet from somebody who was not infected. So this is what they found when they did that. So in order to understand the colors here, so sample A is blue. Remember, that's the one who has infection. Sample B is orange. That's a person who doesn't have infection. Sample B plus A is red. And I think sample C was just the pellet from sample A that they saw what was happening. So they took it out of the culture broth. And you can see that sample C gradually fell away over time. The sample A that was still in the broth, you can see this is day 1, day 2, day 3, all the way up to day 30. Sample A continued to rise, came down a bit, and then continued to rise up here. So by day 30, it's at the highest level. And they are measuring the amount of viral RNA in the stool. But look at what happens to sample B. Day 1, it's at the same level when they added it. This continues to rise by day 30. So they now know that somehow there is capability of the virus to replicate in stool. So your next question is, well, is it possible that you could have cells that are still active? Now, stool is usually dead cells, lining cells. You have bacteria, you have fungi, and so on that are in there. And so the question would be, well, what's making this replicate? Is it actually the bacteria? Because that's what it would look like, because that's what's the highest load in the stool. So then they did another test. So in the sample B plus A, they then got 16 aliquots of it and put different antibiotics in each one to see, well, if this is an infection by bacteria and it kills the bacteria that are causing this, then you shouldn't have any viral RNA after a certain period of time. That's the logic. So that's exactly what they did. And this is what they found. So when we look at the amount of viral RNA load, this is in dark red is pre-antibiotics, and this the kind of dashed line in red is post-antibiotics. Okay, so then they put each aliquot. So like clindamycin here, there was no difference, same amount pre and post antibiotic. When you look at lincomycin, actually post antibiotic there was more. When we look at piperacillin, tazocin, we call that tazocin, there was a decrease post antibiotic. So you can see that there is a difference when you add specific antibiotics. I've highlighted here in red the ones that brought it to zero. Metronidazole, completely post antibiotic. So the pre antibiotic, this is a level, post antibiotic, it drops to zero. The other two antibiotics that do this is vancomycin, drops to zero, and amoxicillin drops to zero. For everything else, there is sometimes a reduction, like ciprofloxacin. It does reduce it, but it doesn't bring it down to zero. There are only three antibiotics that bring it completely to zero. That is very important, because my question is, well, which bacteria are sensitive to all three antibiotics? That's the next question that I had. So, which bacteria would be sensitive to metronidazole, vancomycin, and amoxicillin? So, that's where then we go back to the evidence. So, here we have, and I'm going to show you this in the paper. They were then looking at the different groups of bacteria that were present, and they were trying to monitor what was happening to them. And you can see here, I'll make this full screen. This is again day 0, day 1, all the way up to day 30 in dark blue. So at day 0 here, the Clostridium is at this point here, 4, and by day 30, it's at 7. And this is the sample A that was infected. E. coli starts here, goes up a bit, and then comes down. Helicobacter, no change. Myxococcus, no change. And as you go down here, you then see bifidobacteria starts here, and by 30 days, there is 0. There's another group here, Rhodococcus, absolutely 0 by day 30. So these two are completely destroyed by what it seems to be here, Clostridium. Now, Clostridium here, if you noticed, has probably one of the higher peaks in terms of all the other bacteria. So what it seems is that the infection with SARS-CoV-2 gives the Clostridium an advantage primarily through toxin production. The toxins from Clostridia will then destroy many of these other ones. Even Staphylococcus gets taken out here. Lactobacillus, which is another good bacteria, gets taken out. I don't know what this one is, but you can see the impact. Bacteroides gets taken out. And so that then comes back to the point that somehow the virus, and you have to remember, it's a strange thing, certainly with bifidobacteria, this goes to 0 as well after vaccination. So there is something very unusual about the RNA around the spike protein. Maybe this is what it is. Is it that the bacteria are reading it in a different way? We don't know. But all we know is that it clearly suggests that the bacteria are influenced by the spike protein RNA. And that's why I'm saying that the spike protein RNA, it's whether it's infection or otherwise, it seems to have an impact on bacteria. And specifically, it seems to weaponize Clostridium. So if this is right, what we are likely to be seeing across the world is outbreaks of Clostridium difficile, because people are still getting infected. I know Clostridium difficile, every hospital usually has a limit to how many cases they are allowed per year. It's taken very seriously. But Based on the science around this, we are likely to be seeing these cases rising. It is likely to be a multi-hit phenomenon, meaning that even if the more times somebody is exposed, the greater the risk that can happen over time. And this is why I'm saying it goes back to the principle. You've got to prevent the virus from getting into the bloodstream. So I'm not even talking about autoimmunity now, because normally what I'm saying is that if the virus gets in the bloodstream, there's a risk of triggering autoimmune responses. And this is the principle of storm. And that's when I say the spike triggered autoimmune response mechanism. I've done the presentation for that. Please look out for the links to that soon. But separate from this, we have an issue where the gut gets involved and seems to be weaponized against the host. And the principle seems to be quite simple, is that Clostridium difficile, the characteristic about it is that it produces toxins. So somehow, and I'll just remind you what it looks like. Again, look at it here. The Clostridium difficile at day 0, it's here. By day 30, it has reached its peak, and it peaked from day 14. And that means it was producing toxins and wiping out all the other bacteria and controlling them. And so we then have overgrowth of that. The next phase of their research was to look at the outcomes with antibiotic treatment. And I'll be sharing that paper soon. But I needed to get this as a baseline so you understand where the science is coming from, so that when I then do that recently published paper, you can then tie the pieces together. Now, the problem is we have to be very careful because antibiotics are associated with bacterial overgrowth of Clostridium. And so oftentimes overuse of bacteria drives the overgrowth of Clostridium. And so we have this strange situation where we need to control the growth of Clostridium, but you can't do it with antibiotics. How do you get this back in the box? That's what I'm working out. And as I said before, in order to keep up to date with this kind of science, please make sure that you follow us. Register for our newsletter. It is absolutely free. We'll be able to send you updated information and maybe stuff that we can't share otherwise. So please make sure you register for that. You will get the free ebook about the power of nitric oxide, humming, and the impact that it has on the sinuses. So please join us in this journey. This is revolutionary, difficult things ahead of us, no easy ways out. We have to try and find solutions that can make a difference for everyone else. Have a great evening.